Hello everybody, and welcome back to Abstract Algebra. The plan for today is we are going to be talking about lots of different types of ideals, classifying ideals, whether or not they are generated by an element, generated by a set, whether or not they're principal, whether or not they're prime, and whether or not they are maximal. I've got my usual starts on Monday, 10 o'clock and at 2, in addition to kind of the drop-in session, recitation session at 11. I'm not going to have office hours Tuesday through Friday next week because I figure no one's going to want to really show up. It's Thanksgiving week. Plus, I'm going to be busy with, Thanksgiving stuff myself. So, here's your homework for the week. Your homework is to stay safe, stay healthy, and stay awesome. Yeah, no homework over Thanksgiving. I'm assuming, unless you were watching this before the end of the day on Friday before Thanksgiving, in which case, finish your exam and make sure you submitted it. I'm going to get that graded over the Thanksgiving break. I promise. So, what's the joke of the day? I forgot. Oh yeah, horses may or may not be able to do addition, but why is it a terrible idea in general to try and teach horses geometry? You should not teach a horse geometry because it's a bad idea to put Descartes before the horse. Like that one line? My apologies to the rest of you. So, as a quick reminder, we said that an ideal, S, in a ring R, is just a subring of R, such that if you take anything in the ideal and anything in the ring and multiply them together in either order, you're always going to get something back in the ideal. The subring that absorbs multiplication from the outer ring. And classic example of ideals is NZ in the ring of integers, because if you take something that's a multiple of n and you multiply it by any other integer, you're still going to get something that's a multiple of n. And so today, we're going to be talking about different ways that you can classify ideals. So to start with, let's talk about ideals generated by elements. We could say, given any element, R, little r and big R, where R is a commutative ring, commutative, meaning multiplication is commutative, the ideal generated by R is the ideal of the form R looks like the same notation as the cyclic subgroup generated by R, but in this case, we're talking about an ideal, so a subring, not a subgroup. The ideal generated by R is just going to be the set of all elements of the form A times R, where A is allowed to be any element within the ring R. So in other words, it's the set of all multiples of R within your ring, where you take anything of the form R times something else. Technically, this is a bit of a theorem in addition to a definition. It's a theorem in that we're saying this is going to be an ideal, which might be a fun little exercise for you to try and prove. Hint, hint. So let's take a look at an example. Let's say we wanted to look at the ring of integers, and we wanted to take the ideal generated by some element n. Well, by definition, this is just going to be the set of all multiples of n, the set of all elements of the form n times k, where k is allowed to be any integer, which is just going to give us back nz, set of all multiples of n in the ring of integers. On the other hand, if we wanted to do another quick little example, let's say that our ring this time is R of x. Dr. Gerstle, what's that? So this ring is the ring of all real polynomials. It's a ring we've referred to by this symbol before, this fancy looking P. From now on, I'm going to use this R and then in brackets x to just make it clear we're talking about polynomials over the real numbers specifically. So in the ring of all real numbers, if we wanted to look at the ideal generated by the variable x, for instance, well, this is going to be the set of all elements in this ring of the form x times f of x, where f of x is allowed to be any real polynomial. So what does that mean? What does it mean to say that we're only looking at polynomials that are multiples of x? Well, that basically is the same as just saying we're only looking at polynomials g of x, where g of 0 is equal to 0, i.e. g of x has constant term of 0. So that's what that ideal would look like in the ring of all real polynomials. The ideal generated by x ends up just being the set of all polynomials whose constant term is 0. Because if you're a multiple of x, that means you have to be something like x plus x squared plus x cubed. You can't have any constant terms floating around because then you'd no longer be a multiple of x. How about this one? What the ideal generated by 2 in R of x? Well, by definition, this is the set of all real polynomials that are multiples of 2. So what can we say about the set of all real polynomials that are multiples of 2? Well, we can actually say something diabolical. I claim that's every real polynomial. But every real polynomial is a multiple of 2. So why is that? Well, the reason is because in this ring, 2 is in a unit. Since 2, by definition, is going to be in the ideal generated by 2, and 2 is a unit in this ring. And we proved in the last class that any ideal that contains a unit has to be the entire ring. Mainly because if you have a unit, then your ideal has to contain the multiplicative identity 1, and if your ideal contains 1, then it has to contain anything of the form 1 times r, where r is anything in the ring, and thus it contains the entire ring, because 1 times r is just r. So here, the ideal generated by 2 turns out to just be the entire ring in this case. Every real polynomial is equal to 2 times some other real polynomial, in other words. So that's the ideal generated by an element. It's sort of the ideal ring, it's sort of the ring theory equivalent of a cyclic group. The ideal generated by a single element. But why just stop at one element? Let's talk about what happens when you take an ideal generated by multiple elements, or an entire set of elements. So we can also say that in general, if S is any subset of R, the ideal generated by S is the ideal of the form. We're writing it as this time in our little bracket, in our little, I don't know what you call these things, less than or greater than signs. Instead of just having a single element, we're putting an entire set of elements, where the set of elements is everything of the form A1, S1 plus A2, S2 plus AN, SN, where all the AIs are elements in your ring R, and all of your SIs are elements in the set subset S. So that the ideal generated by a set of things is just basically a set of all finite sums of this form. The set of all things where we're just taking a bunch of elements in S, multiplying by anything we want from the ring, and then adding them together. So let's take a look at an example of one of these. Let's say our ring this time is just going to be the ring of all integer polynomials. polynomials. Not all real polynomials, but all integer polynomials. So something like 2x squared plus 3 halves x minus 5/4 would be an element in the real polynomial ring, but not in this one. And I want to look at the set S that has two elements in it. 2 and x, which are both elements that are in the ring of all integer polynomials. And in this case, if you look at the set generated by S, in other words, the set generated by the integer 2 and the variable x, by definition, this is going to be the set of all integer polynomials of the form 2 times f of x plus x times g of x, where f of x and g of x are allowed to be any two integer polynomials. So in other words, any integer polynomial that can be written as in the forms some integer polynomial times 2 plus some integer polynomial times x is going to be in the ideal generated by S here. So what does that look like? What are the sorts of integer polynomials that will be in this set? Well, this set actually, we can actually write out in a little bit of a simpler way. We could say that it's a set of all integer polynomials, h of x, in the ring of integer polynomials, that satisfy the condition h of x has a constant term in 2z. In other words, h of x has an even constant term. So why is that? Well, if we were to take any integer polynomial f of x and multiply by 2, that's going to have a constant term that's a multiple of 2. Since the whole polynomial is a multiple of 2, the constant term has to be a multiple of 2 if we take anything of this form. If we take anything of that form, that's going to give us polynomials whose constant term is 0. So if we take something with a constant term of 0, add it to something with a constant term of 2, we're going to end up with some integer polynomial that has a constant term equal to 2 as well. Now, Nick, I can hear your thoughts right now. You are currently wondering, but Dr. Gerstel, doesn't this ideal necessarily contain the integer 2? Didn't we say if it contains 2, that's a unit, so it has to be the entire ring? Well, not quite, Nick, because here I made a very, very slight twist to the example we did right before this. I changed the ring to be the ring of all integer polynomials. And what that means is that 2 happened to be a unit in the ring of all real polynomials, so any ideal containing 2 would have to be the entire ring of all real polynomials. In the ring of all integer polynomials, 2 is not a unit, and so this doesn't have to be the entire ring of all integer polynomials. Because 2 would have to have multiplicative inverse of a half, which is an element in the ring of all real polynomials, but is not an element in the ring of all integer polynomials. So that's what it means to take an ideal generated by a set. We're not going to do too much with these. I just kind of wanted to have this example to look at where we take an ideal generated by 2 elements. And yes, who do I want to take on? And yes, Lauren, you can have subgroups generated by multiple elements in group theory. We just didn't talk about how to do that, but it's basically doing something similar to this. So that's what it means to take the ideal generated by an element or a set of elements. Now let's talk about what it means for an ideal to be principal. A principal ideal is basically the same thing as a cyclic subgroup. An ideal is principal if it can be generated by just a single element. So ideal S in R is called principal. I don't know where it got this name, but that's what it's called. If S is equal to the ideal generated by little s for some little s, and big S. So if it can be generated by a single element, then that ideal is a principal ideal. Let's see if we can look at an example. Let's take the ideal generated by 2 and x. Is that a principal ideal? I think that's a fair question to ask. Can this ideal be generated by a single element? What's that, Nick? You're wondering what ring we're working over? Ah, very clever. Yeah, well, let's check over the two polynomial rings we have, the ring of all real polys and the ring of all integer polys. I'm saying poly because I'm apparently too lazy to say polynomial. And the ring of all integer polynomials, is this ideal principal? Well, I would say no. 2x can't be generated by a single element. Because the only way to get all integer polynomials whose constant term is even, all integer polynomials whose constant term is even, only way to get all of those in an ideal generated by one element is if that element is a unit, which would then have to give us the entire ring and not just this ideal. Would be to use a unit, which would give us all of the integer polynomials. So in other words, there's the only way that we can get all polynomials whose constant term is even. The only way to do that with a single element is to take a unit. But if we take a unit, then we're going to necessarily end up with the entire ring and not just this ideal itself. But Dr. Gerstel, why can't we just take the ideal generated by 2 here? Well, if we take the ideal generated by 2, that's not going to give us the same as the ideal generated by 2 and x, because the ideal generated by 2 and x would include the element, let's say, x plus 2, because that's taking something in this ideal plus something else in this ideal. But x plus 2 is not going to be an element in the ideal generated by 2, because x plus 2 is not a multiple of 2 within the ring of all integer polynomials. So in the ring of integer polynomials, the ideal generated by 2 and x is not a principal ideal. What if I ask the same question, though, in the ring of all real polynomials? Well, in the ring of all real polynomials, the ideal generated by 2 and x contains the unit 2. In this ring, 2 has a multiplicative inverse, just a half. So that's going to tell us that the ideal generated by 2 and x is going to be the entire ring. Can the entire ring be generated by one element? I think it can. Can be generated by 1. Because the ideal generated by 1 is the set of things you would get when you multiply everything in the ring by 1, which is just going to give you everything in the ring, because multiplying by 1 doesn't change anything. So in this case, the ideal generated by 2 and x is principal. Or for that matter, the ideal generated by just 2, because that'll also give us the whole ring. So in this case, this ideal ends up being principal even though it doesn't look like it. Looks like it now it's being generated by two elements. That's not principal. But in fact, adding x to our generating set doesn't change anything. Just having the ideal generated by 2 alone already gives us the entire ring. So having the ideal generated by 2 and x, well, there's nothing to add to that. We're still going to get the entire ring. So the moral of the story, is the ideal generated by 2 and x principal? It depends on what your ring is. It is principal in the ring of all real polynomials. It's not principal in the ring of all integer polynomials. So you got to know what your ring is. Depending on what your ring is, it may or may not be principal. So that's a description of kind of what principal and ideals are. Let's move on to talking about prime and maximal ideals. So a prime ideal, or let's say an ideal S of R, is a prime ideal if given any two elements, A and B, in the ring R, such that A times B is an element in S. Either A has to be an element in S, or B has to be an element in S. So, in other words, your ideal is prime if the only way to have a product of two things being your ideal. Oh my gosh, there's someone out the window. That's terrifying. You can't see them, but they're just, I don't know, doing something right outside. It's creepy. Anyways, ideal is prime if the only way to have the product of two elements be an element in your ideal is if at least one of the two elements to begin with was in the ideal. So let's look at an example. I want to look at the ideal 3z in the ring of integers before you ask it. I claim 3z is going to be a prime ideal. And why is that? It's going to be prime because anytime you take two things and get a multiple of 3, if x times y is in 3z, meaning if x times y is a multiple of 3, either x had to be a multiple of 3 or y had to be a multiple of 3. Or both. When we say either this or that, it could potentially still mean both. So the only way to have two things multiplied to give you a multiple of 3 is if one of the original two things was a multiple of 3. Let's compare that with the ideal 4z in the ring of integers. Well, I claim 4z is not a prime ideal. Why is that? Well, it's because we can take two things that are individually not multiples of 4 and get their product will be a multiple of 4. And in particular, let's go with 2 times 6. 2 times 6, I would argue, is an element in 4z, because 2 times 6 is 12, and 12 is a multiple of 4. But 2 is not an element in 4z. 2 isn't a multiple of 4. It's a factor of 4, but not a multiple of 4. And 6 is also not in 4z. So in other words, in the ring of integers, 4z is not a prime ideal because it's possible to take two things not in the ideal and have their product give you something in the ideal. Whereas in 3z, there's no way to have two things that are not multiples of 3 suddenly multiply to give you a multiple of 3. That's impossible in 3z, but totally possible in 4z. And that's going to make 3z a prime ideal, whereas 4z is not a prime ideal. 3z is a prime ideal, 4z is not a prime ideal. wonder if that could possibly have any relation to 3 is a prime number and 4 isn't. Nah, must be imagining things. Let's talk about maximal ideals. We're doing on time. Doing great. So a maximal ideal is just an ideal that can't be any bigger unless other than by taking the entire ring. So S and R is a maximal ideal. And S and R, we're assuming S is an ideal to start with. I'm just being lazy. If whenever T is an ideal in R, with S is a subset of T, and T is a subset of R, either S equals T equals S, or T equals R. So this means, in other words, the only way to get an ideal in your ring that's bigger than S, that if your ideal is contained in some other ideal, that other ideal has to either be everything in the ring or just S again. There's no way to take an ideal that's bigger than your maximal ideal, but also smaller than the entire ring. It's as big as it can get without encompassing the entire ring. So let's look at an example. I'm going to look at a ring of all integer polynomials, and I want to take the ideal generated by x. I'm looking at the dust storm outside the window. What the heck is going on? You can't see it. You're not interested. Is the ideal generated by x going to be a maximal ideal in the ring of all integer polynomials? I claim the answer is no, it's not, because there is an ideal that's bigger than the ideal generated by x, but also is still not the entire ring. And that, of course, being the ideal generated by x and 2, which we've seen already in this class. So this x, the ideal generated by x is not maximal, since x, the ideal generated by x is a subset of, but not equal to, the ideal generated by 2 and x, which is a subset of, but not equal to, the entire ring. By the way, this symbol right here means it's a subset of this. This is a subset of that, but they're not equal. It's a proper subset of them. So the ideal generated by x is properly contained in this other ideal generated by 2 and x, which itself is properly contained in z of x. Meaning, it is possible to have an ideal that's bigger than this one, but still not the entire ring, and so that tells us this ideal is not maximal, which is sad. All right. How about this one? How about the ideal generated by 2 and x? I claim this one is maximal. And the reason being, the only way we could add something to this ideal to make it bigger is to add a polynomial with an odd constant term. Since adding any polynomial to this with an odd constant term in other words, any polynomial that's of the form, I don't know, x times f of x plus 2k plus 1. Because any polynomial that has an odd constant term has to be something of this form. So the piece of the polynomial that has x's in it, and then a 2k plus 1 odd constant term at the end. So if we were to add any polynomial of this form to our ideal, which something of this form is the only thing we could add, because the ideal generated by 2 and x already contains literally every other integer polynomial. We're only missing out the ones with odd constant terms. And if we were to have this ideal and this element in it, if we were to add that element to our ideal, we would also add, in order to be, still closed as a subring under addition and multiplication and such, that new polynomial, x times f of x plus 2k plus 1, which we're now assuming is in the new ideal t, plus x times negative f of x, which this is going to be, by definition, in the ideal generated by 2 and x, which hence would have to be in t, plus 2 times negative k, which is also going to be in the ideal generated by 2 and x, hence in our new ideal t that we're forming. We're forming a new ideal t by adding some polynomial with an odd constant term. Well, here's the thing we're adding. We also will have to have this element, x times negative f of x, because that's in the ideal generated by 2 and x by definition. This is in the ideal generated by 2 and x by definition, since it's a multiple of 2. This one, since it's a multiple of x. If we add those up, we'll get x times f of x plus 2k plus 1 minus x times f of x minus 2k is going to be 1, which will be in our new ideal t. And since 1 is a unit, that's going to imply t has to be the entire ring. So in other words, there's no way to make the ideal generated by 2 and x any bigger while still keeping this to be an ideal, meaning something that's closed under addition. There's no way to make this ideal bigger without making it the entire ring. And that tells us in turn that the ideal generated by 2 and x is maximal in the ring of all integer polynomials. This is a bit of a complicated example, but I wanted to use this ideal we've kind of been building up through class today, ideal generated by 2 elements. And the reason this is maximal is if we were to add anything to it, make it any bigger, we would have to add at least one element of this form. Because any odd polynomial whose constant term is odd has to look like this. This is the part with all the x terms in it, and then the constant term will have to be something of the form 2k plus 1. Because every odd integer looks like 2k plus 1 for some k. So if we're adding anything new, we have to add something that looks like that. But if we add that, we would also, in order to be closed as a subring, which is necessary in order to have a new ideal t, we would have to have that new thing we're adding plus x times thing plus 2 times thing. Because these are both elements in the ideal generated by 2 and x, and so would have to be in our new ideal if we're just making the old ideal bigger. But if we add that, that implies we would also be able to show that 1 would have to be an element in our new ideal, and since 1 is a unit, that tells us that our new ideal has to contain everything. There's no way to make the ideal generated by 2 and x bigger without adding literally everything in the integer polynomial. All right, how are we doing? So, last thing I want to do for today is I'm going to give you all an exercise to think about. It's on the next 2 pages. I'm giving you a bunch of examples of ideals in rings. And I want you, for each of these examples, to tell me whether the ideal in the ring is prime and or whether it's maximal. Go ahead, take a couple minutes and look at each of these examples. See if you can determine which ones you think are prime, which ones you think are maximal. I'll go ahead and write those out on the board here. So first example, our ring is the ring of integers. Our ideal is 6z. Second example, our ring is the ring of all integers. Our ideal is 7z. Third example, our ring is the ring of all real polynomials. Our ideal is the ideal generated by x. And last, we're going to look at the ring of all integer polynomials, ideal generated by x. So for each of these examples, tell me whether or not the ideal is prime and or maximal. Please pause the video while you think about this. know you didn't pause the video. You pause the video now and think about this. Don't just skip ahead, please. Right. All right, good. Now you've all had a chance to think about each of these, and we can kind of go over each one. 6z, I would claim, is that a prime one? Well, I would say this is not prime. And no, you can't say it's not prime, Dr. Gerstle, because 6 isn't a prime number. We don't know that that implies the ideal is not prime. Yuck. But I would say this one's not prime because we could say that 2 is not an element in 6z. 3 is not an element in 6z. But 2 times 3 is an element in 6z. Because 2 times 3 is 6, and 6 is clearly a multiple of itself. 6 times 1. But 2 and 3 are not multiples of 6, but their product is. That's enough to tell us this ideal is not prime. Is it maximal? Can we find any ideal in the ring of all integers that contains 6z properly, meaning every multiple of 6 is in this ideal, but the ideal contains more, and that ideal is not just the entire ring? I think we can, specifically with 2z, or with 3z for that matter, meaning this ideal is not maximal. The reason being, if you have a multiple of 6, anytime you have a multiple of 6, you automatically have to be both a multiple of 2 and a multiple of 3 as well. Meaning everything in 6z has to be contained in 2z as well as 3z. But these are also ideals that are not equal to the entire ring, so we can make 6z a bigger ideal without making it the entire ring. That's enough to tell us 6z is not maximal. So how about 7z? Is 7z prime ideal? Why, yes, because 7's a prime. No, Josh, not because 7 is a prime number. So the real reason is because we can say if a times b is a multiple of 7, it has to be the case that a is a multiple of 7 or b is a multiple of 7. Dr. Gerstle, how do we know this for sure? It's a little bit hard to actually prove that. We will prove that later on in this packet, though. We'll have a better way of determining whether or not an ideal is prime. That'll make a lot more sense, and you'll say, oh yeah, 7z has to be prime. But is this ideal maximal? I guess I just gave it away by writing down maximal without the word not in front of it. Turns out 7z is a maximal ideal. Because we can say if we have some ideal 7z is contained in an ideal t, which is contained in the ring of all integers, we can say t has to be 7z or t is the entire ring of integers. And the reason for this is 6z, if you notice, can only be contained in ideals generated by elements n that are factors of 6. So 2 is a factor of 6, therefore 6z is contained in 2z. Because anything that's a multiple of 6 automatically has to be a multiple of any factor of 6. So like 2 and 3, etc. Problem with 7z is 7 doesn't have any factors other than 1 in itself. So anything of the form, any ideal that contains 7z would have to be generated by a factor of 7. But if it's generated by 7, then it's just 7z again. And if it's generated by 1, then it's just the entire ring of integers. There is no ideal bigger than 7z, but smaller than the entire ring. So 7z is maximal and prime, whereas 6z was not prime and not maximal. What about this one? The ring of all real polynomials, and the ideal is the ideal generated by x. Is this prime? I think it is. The reason being, we can say that if f of x and g of x, if f of x times g of x, I should say, is in the ideal generated by x, then that by definition means f of 0 times g of 0 is equal to 0. Because one way to write polynomials in the ideal generated by x is to say they have a constant term of 0 or when we plug in 0 into the polynomial, we would get 0 as an output. So if f of 0 times g of 0 is equal to 0, that's going to tell us, since the real numbers are an integral domain, that's going to tell us that f of 0 is equal to 0, i.e. f of x is in the ideal generated by x, or g of 0 would be equal to 0, which would imply that g of x is in the ideal generated by x. So in other words, anytime you take the product of two polynomials in the ideal generated by x, and that's in the ideal generated by x, it has to be the case that at least one of those two polynomials is also in the ideal, which means ideal generated by x going to be prime in the ring of all real polys. By the way, the exact same argument shows that the same ideal is prime in the ring of all integer polynomials by the exact same reason. Or why not pointing up there? You can make the exact same argument. The integers are also an integral domain, just like the reals are. So just replace the exact same argument here. Will also tell you that the ideal generated by x is prime in the ring of all integer polynomials. So here, we know that the ideal generated by x in the ring of all integer polynomials is not maximal. So why is that? Why is the ideal generated by x not maximal in the ring of all integer polys? Well, the reason is, we already talked about that. It's right here. It's not maximal because it's contained in a bigger ideal, the ideal generated by 2 in x, that's not equal to the whole thing. How about the ring of all real polynomials? Is the ideal generated by x going to be maximal or not in the ring of all real polynomials? So here, I'm just going to expand this one out and erase that one. Go back a few seconds in the video if you were still looking at it. Well, the only way to add an element to the ideal generated by x in the ring of all real polynomials is to add some polynomial whose constant term is non-zero. If this ideal already contains all the polynomials whose constant term is 0, to add something new, we would have to add something whose constant term is non-zero. Something of the form, and if your constant term is non-zero, that means that your polynomial is equal to something of the form x times f of x plus some k, where k is non-zero. So we have to have, any polynomial whose constant term is non-zero has to have form x times f of x for some f of x, where this is the part of our new polynomial that has all the x terms in it. And then the constant term, non-zero constant term is just going to be some k not equal to 0. But here's the catch. In this new ideal t, though, we also have this polynomial, x times f of x plus k. We would also, this we're assuming is in the new ideal t. We also have to have x times negative f of x. Why? Because that's an element in the ideal generated by x, which is also contained in t. So if this is in t, then t also has to contain x times negative f of x. And because t is an ideal, it has to be closed under addition as a subring. So it has to contain, what are we going to get? We're going to end up with k. But k is non-zero. It's a non-zero constant in the ring of all real polynomials. But we know something about that then. We know in the ring of all real polynomials, any non-zero constant has to be a unit. But since k in the ring of all real polynomials is a non-zero constant, K is a unit, hence T, which is our ideal containing the unit K, has to be equal to the entire ring. So what does that tell us then? The only way to make this ideal, the ideal generated by x, bigger in the ring of all real polynomials is to take the entire ring. There's no way to make it bigger without giving us everything. That's going to tell us in this ring, the ring of all real polynomials, the ideal generated by x is maximal. It's not maximal in the ring of all integer polynomials, because there's this ideal that's bigger than it, but not equal to the whole ring. But the same ideal is maximal in the ring of all real polynomials. Remember, in the ring of all real polynomials, the ideal generated by 2 and x would be the entire ring, so this counterexample wouldn't work to show it's not maximal. So what did you notice? In every case that we got a maximal ideal in these 4 examples, the maximal ideal also turned out to be prime. In most of the cases, all the prime ideals were maximal, with the exception of, I erased it, with the exception of this one. And the ring of all integer polynomials, the ideal generated by x was prime, but not maximal. So it looks like we have some evidence to suggest all maximal ideals may be prime in all the examples we've seen, but not all the prime ideals we've seen are maximal. In the next class, meaning the class Monday after the break, we're going to explore that further, and in fact, that's exactly what we're going to prove. That anytime you have a maximal ideal, it has to be prime, but the vice versa is not going to be true. Prime ideals do not have to be maximal. How are we going to prove that, Dr. Gerstle? We're going to prove that using everybody's favorite technique. We're going to prove it using quotient rings. All right, that's going to do it. Hope you all have a good Thanksgiving. Remember your homework. Stay safe, stay healthy, stay awesome. Try not to take necessary precautions when you're around family. I know some of you are just going to go, yeah, whatever, Dr. Gerstle. But seriously, you don't want to infect your family, especially because some of you probably are going home with COVID. Take all necessary precautions. Even if you don't think you have COVID, just please try and keep everyone safe. All right, take it.